Hello and welcome back to my lab. Today we're going to finish up all of this whiteboard stuff here. So I have a new pen pusher that I designed. It's in pieces now, but we should be able to assemble it and take a look at that. There's also some things I want to fix on the horizontal pulleys. We'll get into that in a minute. And then after that, we can go ahead and take a little bit of a dive into the software setup and some code we made just kind of for the fun of it. You'll see all that later. But first, let's go look at the pen pusher. All right, it's in pieces right now. I'll probably show you a bit of CAD over here if I can. And then hopefully that makes a bit more sense. But we're going to go through each individual piece and what it does. For reference, these are off of a new printer we got. It's a cheap $400 printer to see if we like the SLA printing style. It uses a bath of resin and a UV cure light and pulls it up out of the bath. You can look up SLA printing if you want to see it. We might actually invest in a better one of those later. I'm liking it so far, but the downside with the $400 printer is that we have some dimensional stability issues. So we're going to have to probably do a little bit of cleanup on these to get them just the way I need them for the design. But these are way better than what we had with the previous design. So now we're going to use this DC servo motor, the same kind that people use on their remote control airplanes and remote control cars and stuff like that. It's a lot stronger. It's just a DC motor geared down. This is going to give us a lot more control and power than that solenoid. The whole thing got kind of janky that way. So we're just going to use this DC servo, and I just gave it a little bit of a gear arm, so to speak. And this is just going to fit on the carriage plate here that I pulled off the machine. I've been doing a little bit of testing, but this fits right on there. I've got some mount blocks and everything that I'm going to put those on with. And then let's see if I can fit all this together without screws so far. This is going to hold some rail that we've still got to cut and put in there. And then on that rail, I've got linear bearings. And I don't know how well you can see it, but I've got a little rack for this gear to go up and down against. So this will push and pull this element, which interacts with this right down here. Let's see if I can hold all this together. This element down here is actually going to be what holds the pen or the marker. And I'm just going to move this because I can't hold it all at the same time. But you can see this element is going to go up and down on rails, and it'll pull the marker up when I want to pull it up. And when it goes down, it's going to, the hard linkage here is going to let the whole thing go down, but it will push it through springs that are going to go between the elements there. And that should allow me to apply some pressure to the pen, but it's going to ride on the surface. And so this might end up being a bit over-engineered, but it's really fun and I can't resist. So we're going to give it a go. Either way, it's going to be a lot more deterministic and powerful than what we had, and therefore a lot easier to control in the software. Speaking of controlling this thing, our motion controller is going to be based on 24 volts because that's industrial standard stuff. However, this hobby DC servo right here is expecting something like 5-6 volts to drive it. So what I've got to do is take that 24 volts from the box and convert it down to 5 volts, and then I'm just going to run that into a little Arduino and then use the Arduino to take a 24 volt signal through, well, an opto-isolator, if you know what that is. Just a little signal conditioner to bring down that 24 volt signal to a 5 volt signal, and then the Arduino is going to generate a pulse width modulated signal. If you also know what that is, that's a topic for another video, but that is the signal that this thing needs in order to define its position. So we're turning a digital signal from the 24 volt controller into a 5 volt PWM signal. I really only need to hard code 2 positions into this thing, so it's just going to toggle between these 2 positions when it gets the signal and when it loses the signal. And that should just simply run this guy up and down once it's all put together. It's just a bit too much for me to hold together with just 2 hands. but it'll work a little bit like that. All right. But before I can get this all to fit together, I've done a little bit of testing, as you can see, but there's some finishing I have to do on these parts. So let's go ahead and montage that, and then we'll assemble it and come back to it. All right, after a bit of finaglery, all of this is together and fits reasonably well. The only real problem I had was with the bracket, I guess I'll call it, the main structure of this assembly. The hole placement, I was trusting the 3D printer a bit much, and it didn't really work. It wasn't holding the bars parallel with each other and a couple other issues like that. So what I ended up having to do is drill these out and make them just too big so they can move around. I got them everything lined up, held everything all at the same time, and then I had to use, I packed it in with a little bit of the shavings from the plastic and then filled it with super glue. So sometimes these are the things you got to do when you're prototyping. But now I got them all parallel and everything, and that works. So yeah. At some point, I definitely want to get a better printer, one that doesn't bleed the way that the UV cure resin is exposed, lets it bleed out, and as the longer it's exposed, it gets a little bit bigger, and yeah, there's kind of screws with your tolerances a bit. But anyway, now that everything's working, sanded so that it fits together right, we're ready to go ahead and test it. So right now what I have it set up with is just the power supply here is going to give us 24 volts. That's going to power the Arduino and everything in here. And here's my signal. So I'll just touch the signal to the 24 volt supply, which will give us the digital input as a simulation from what we'll get from the main controller. So what you should see is it's just going to toggle from the low state to the high state back and forth. So let's go check that out. All right, so it's in the low state, and there we go. And I think it's traveling a little too far, or it's trying to travel a little too far, so I just got to modify the set points a little bit, but other than that, it seems to be working just fine. So once we get this on the whiteboard, I can put a marker in there such that it's just lightly pressed against the whiteboard when it's down. and then fully retracted when it's up, and that should work just fine. And it's reasonably quick. I could probably shorten the throw of this quite a bit, because I mean, you can get really close to the whiteboard without touching it, so we could make the transitions quite a bit faster and probably increase the whole speed of the operation. So I'll play around with that when we get around to it. And I think that's everything. So I'm going to go ahead and get this mounted back up on the machine, and then we can move on to the horizontal belt tensioning mechanism and what we have to do there. As a bit of review, this guy here, I designed this whole assembly, and it serves three purposes. It's of course the opposite side of the belt to keep it straight. It's an end stop for the carriage, and it also tensions the entire belt. And because it's trying to do so many things, I've run into some issues, which, you know, I was kind of asking for. So this here, let me see if I can push it in and out and you can see. This one's the worst one. I had the worst tolerances on this one when I was cutting it on the mill, and you can see that it doesn't actually hold this straight. It pops out because there's so much tension on this belt. It's using, you know, through this little lever arm, it's going to pull this around. And the issue with that is that you can actually use somewhat off-angled pulleys to sort of drive a belt left or right. And normally, like in a belt sander, you use that to center the belt. Well, here, because it's just off-angle by a degree or two, it's causing that belt to just run right into the wall. I don't know if you can see this very well, but the wall and the pulley, it's trying to ride up that wall and giving me very uneven and unpredictable resistance to rolling, which causes a lot of problems that the servo motor could punch right through. But the issue is these servo motors, they auto-tune. They automatically try to throw the carriage back and forth to get a feel for how the axis is, and the auto-tuning algorithm just cannot handle that kind of non-linearity, the weird behavior that this causes, because the faster it goes, the more this issue arises, and it's a very strange dynamic that it's not expecting. Unfortunately, there's no manual tuning. Normally, if I ran into this issue with a normal servo motor, I would just start manually tuning it, and it wouldn't be that big a deal. I mean, I'd fix this also, but I'd manual tune it. So I've been thinking about how to kind of just fix this retroactively while maintaining that adjustability. And I think the easiest way I'm going to be able to do that is just take this upper block here over to the mill, kind of mill off some of this in the back, and then put a rather large tapped hole for a screw, and I'll be able to just tighten that screw down and push it against the wall. And that way, if I need to adjust it, I can back the screw off, adjust it a bit, and then tighten it back down. So it's not the greatest design, but I think that might work for us. It'll at least straighten out this belt a little bit, hopefully reduce that issue to the point where we can go a little bit faster, because with the servo not tuned as well as it could be, we're really not able to get the speed out of it we could otherwise get. So I'm going to go ahead and take these off the wall here and bring them over to the mill, and then we'll do some things. Okay, so in case it didn't make sense while it was on the wall, here's the part we're looking at. So from the side that we saw, this is the belt tensioner here. From the view kind of inside the wall, you can see that this piece just fits into a slot that I milled out. So this really isn't important. This is the piece we want to fix really quick. I'm thinking of just adding a little screw right here. So that'll press into the shank, whatever you want to call it here, and just keep it pressed against the wall. So that's all we're really doing. So I'll go ahead and get this in the vise, and we'll move on with that. All right, and that seems to work. So all the slop is taken up. It's firmly against the back plate like my design intended. So I think that's going to work. Already running it back and forth, I can feel like I can feel that I can go faster before running into that issue. It looks like I might have to tune the other side because there's a little bit of adjustment in the other shaft, kind of back and forth, so I can steer it a little bit. I had it steered all the way to try to compensate for this issue. So I'm gonna have to kind of take that system apart, move it over to now compensate for the much lower issue we have here. And then we might be able to get a lot more speed out of it that way. So I'm going to go ahead and do that and then put the rest. There's some other stuff I got to put together, and then we can go ahead and test to see how the performance has changed. So I'm going to go ahead and do that. Okay, I got everything mounted here that I need to get mounted. This is all ready to go. I also went ahead and tried to tune the angle of the shaft here, but after kind of wiggling it around, I can see there's too much play in that system to really do anything, and I wasn't able to tune out that dynamic resistance that's caused by the belt running up against the edge. So it looks like that is not going to be able to run very fast, at least in its current configuration. The motor here has plenty of horsepower to move everything we need to move, but its torque is too low to overcome those periodic humps. I mean, it can overcome it, but it can't control it very well because I'm dipping into a sort of torque reserve. For every servo motor, there's an amount of torque it can do all day long, every day, and there's spike ratings for peak torque. And we're going into the peak torque sector in order to handle just moving along because of these resistance spikes. So this motor here can spin at like 3,000 RPM. So the easy way to solve this is to put a gearbox right here between the business end and the motor itself, and that would solve that problem. Those are kind of expensive, so typically I avoid them, and I haven't actually been able to find a nice hobbyist solution for gearboxes. But still, I want this to run properly, so I might try to source a gearbox for this. If I do, we'll make another video on that, but I think for now we're just going to consider this done, and it's going to just kind of run a little bit slowly. The vertical axis is just fine, so that doesn't have any resistance issues. So when we run this, you'll probably notice the vertical axis is no difficulty controlling, but the horizontal is a little bit derpy right now. But given how much I was reaching on this design, I'm kind of surprised that it works at all, so that's probably pretty good. With all that said, I have a G-code for a test drawing for this thing, so let's go ahead and run it and see how things look. Okay, so it's all ready to go now, except that the marker is not in there yet. To put the marker in, I activate the marker pressed down bit. That pushes everything down towards the whiteboard, at which point I can take the marker, place it in the holder until it touches the whiteboard. And what I'm going to do is press up against the spring, and then, hold on, I need my, there it is. I press up against the spring and tighten it down. Now we should be good to run it. Yeah, so you can see that wobble I was talking about. I don't think I'm going to be able to stand that for very long without getting a gearbox, so we'll see how that goes. But as far as this test goes, I've got a bit of text up above here, a couple of text pieces down here, as well as an orthographic view drawing of one of the CAD elements. Actually, it'll be the carriage here. So you'll see that once it's done. Seems like it's chugging along just fine. So we'll go ahead and check up on it when it's further done. Aha, here it is. It's a little bit slow, it's a little bit wobbly, but it did it. I mean, here's basically my first use case. If you remember the Skittle sorter back in well, the day, I was trying to draw some diagrams of the plan, but it was all terrible, and I ended up not using this at all because my writing is not good enough to be very useful. But here, I can draw these nice little check boxes here, so that's pretty cool. So this, we should have many uses for this in the future. Sometimes we can just make the whiteboard look cool, and sometimes we can use it to create these kind of diagrams, which are a little bit more useful, especially when there's people in the lab here that we want to show stuff to. So in that regard, it's very useful. You can see the wobbly lines. You know, anytime we do a big XY move at the same time, you can see how the x-axis falling behind becomes a bigger problem because the y-axis has no problem, so it expects the x-axis to be able to follow along, and you get these issues here. If we do put a gearbox in there, that would be greatly cleaned up, and we'd probably be able to go a bit faster. We'd be able to crank up the accelerations and stuff like that. I don't know exactly where the limit of the frame, being the wall back here, the wood studs, that really is the great limitation of this machine, which I kind of thought it would be the belts fundamentally, but the belts seem to be fine. It really is the wall behind the belts that's causing the issue, which of course makes perfect sense because they're not going to be rigid at all. So any kind of bending and flexing. I did notice one time I ran the vertical axis up against a hard stop, which if you think about the way that the tension goes, if you push any further into a hard stop, if you push that, it will essentially create force between these two rails here, and I was able to see the entire wall flex just from the little servo that we have on the axis here. So I think that's acceptable given the conditions. I think this draws fast enough that it would be useful to me. I can generate the G code for it and then get it started and just walk away and work on some other stuff while it's drawing. So I'm pretty excited. That's actually pretty cool. I can come up here and actually write on the board about, you know, if, you know, this is bad, or man, my handwriting is bad. Oh no. I can't write even well enough to annotate.
Like, oh, right.
Oh yeah, my handwriting is terrible. I forgot.
Let me go program the computer.
Hold on. I'll be right back. Yeah. And now that we've tested this CNC controller, I'm comfortable with it, and I think it would be good enough to put on the milling machine when we get around to doing the CNC on that. That's half the reason of doing this project, was just to get used to the ClearPath motors plus the CS Labs CNC controller, the CS Mio, I think it's called. I don't know if they actually pronounce it that way, but that's what it's called. That controller. So I like that, and we'll see if we can use that over on the mill later, whenever I get the funding for that. So this is essentially done, but let's take a look at one more thing before we conclude the video. I want to take a look at how we created the G code for this, because coming into this, I thought that the generating G code from drawings was going to be kind of a solved problem by now, but it's not actually as straightforward as I thought it was going to be. So let's go ahead and take a look at that on the computer. I didn't have a ton of time to look into how to do this, so I'm just going to show you what I did, and if you have a better way, then let me know in the comments. The first thing I did was export my Fusion 360 drawing as a PDF, and then this can be brought into Inkscape here. In Inkscape, I'm going to clean up the stuff I don't want, and then set the canvas to the size of the whiteboard so that I kind of have a reference to place the drawing. Put it where I want, and then use the G-Code Tools library here to set up a tool. It's a little weird how it works in here. It makes this little card and then you set the parameters of your tool in this card. It's very strange, but that's how it works, so we'll do that. Once that is set up, I can use this path to G-code tool here, and that will go ahead and generate the G-code. Now, whether or not this is actually appropriately formatted for your CNC is something you'll have to check out, but this did happen to work for my machine here. So from here, I was going to show you more about the actual CNC control software, but I can see this video is getting pretty long, so I'm going to go ahead and make another video about that and call this one done here. With all this said, thank you for watching, and we'll see you next time.